Okay, welcome everyone. This is the week 7 webinar. So we're past halfway through the class now. So we're moving forward, which is good. And the plan today is, as always, I'll answer any questions that you might have, and I'll do that at the beginning, but I'll do that throughout as we go. And then today is actually day 1 of the rest of the class. Pretty much just about everything we do from the rest of the class is going to be hypothesis testing. Okay, there's one little thing that happens other than that, but pretty much that's what we're doing. So today is the introduction to hypothesis testing, what it's all about. And I'm going to start out. This is one of those where I have a list of items, but it's more than just a list of items. This is ordered. And this is the order at which you do hypothesis testing. And you really don't do it in, very different orders. There's a couple things you can do at the same time, but the ordering is really important. And the first thing I'll talk about are the null and alternative hypotheses. So that turns out to be really important. Then I'll talk about the type 1 and type 2 errors. So if things go wrong and your sample didn't really represent the population, even though you thought it did, then what things go wrong? What damage is done? Sometimes I'll say, what are the repercussions of the type 1 and type 2 errors? Then we'll talk about the level of significance. And that's kind of similar to the confidence level, but it turns out for some reason, I have no idea why, for confidence interval statisticians are worried of, they want to, be 95% certain that they're right. For hypothesis testing, for some reason, you say, I want to make sure that I don't have more than a 5% chance of being wrong. And it's just for some reason it gets switched. And don't yell at me for this one. It's just what everyone does. Then I'll get into the p-value. Okay, the p-value is going to be a very important number that's going to help us decide whether or not we can say we were right, or maybe we're going to say, well, we don't have enough information to say we're right. So that's what a p-value is going to do. And we're going to state the conclusion, which is basically you're going to conclude we were right, or we don't have enough evidence to say we were right. And we'll talk about the language to make that happen. Then I'll talk about interpreting these things, interpreting the p-value. And this is a little bit like interpreting the confidence level in that it's not that easy. It's pretty sophisticated. Okay. And I'll give you a template. We'll do some examples and you'll see how that works. And we'll also interpret the level of significance. Same idea. Okay, then after that, I'm going to start talking about project 2. You're not quite ready to do project 2 yet, but you might be ready to start thinking about it. That's about it. Okay, and hopefully you have partners, but you might be ready to start thinking about it. So I'll talk about planning project 2. Really, you need to know chapter 10 to be able to fully do project 2, because project 2 is all about chapter 10. But if you don't know chapters 8 and 9, you'll have no chance of even understanding 10. So after this chapter, it's really the time to start thinking about project 2. So that is the plan for the day-to-day. And this is an odd week. And what's relaxing about an odd week? We're in week 7.
No exam.
Yeah, there's no exam. So there's no exam to do. Don't worry about it. That's why I can start talking about the project a little bit, because you should at least start thinking about it. You're not ready to do it, but you can start thinking about it. There's no exam. It's kind of a lighter week. And I will let you know that I did grade. Hopefully you got notifications. I did grade both your discussion posts and your exams. So today was a very busy day, by the way. I basically graded, and then taught. Haven't had any time today. But tomorrow, I'm going to have a nice little bit of break where I'm going to play a little bit. It'll pretty much an all work day from morning till night. But that's because I graded, I got it done. And again, you want to take it seriously. We're now, I believe it might be exactly 50% through the course in terms of points for your course grade. Okay, so now you know where you are at the halfway point in course grade points. So that's just a big note. Any questions at all about anything? I'll be happy to answer. Any questions? Not hearing them. Okay, but again, always feel free to put what your questions are in the chat box, or to just say your questions, and I'll help you out with that. And just remind you, it's always recorded, which I think you get the up, and I put it up on YouTube, so it is public, but your chat box is not public, and I don't mention your names in the webinar. Okay, so if there's no questions, let's talk about hypothesis testing. And I want to do what I consider, and you probably will consider, the most important thing that has been dealt with statistics-wise in the past several years, and that is COVID vaccination. Okay. And I'll let you know, I look at it. So the question is it possible to get extra credit? So there's no extra credit in this class. Okay, there isn't any extra credit, but there's still, a lot more stuff going on. We're only 50% through, so it means you can work hard and do well on the rest of the stuff by spending extra time on it. So I don't do extra credit, if you're wondering. So it's just regular points. So sorry about that, but there's still a lot of stuff left. Okay. So you probably agree that the vaccination was important. Okay. And when you think about it, what happened? What happened is, Pfizer and Moderna and J&J, they came up with their vaccination. Okay. How did they know it worked? Any thoughts? Trial and error. Okay, and what does that exactly mean? And that's what we're going to be talking about now. Okay, again, this is like worldwide important. Okay, it's like really, really important. That's why I'm bringing this up, because that's how important this was. Okay, so what it was is they came up with the vaccination. Okay, and it's funny, they couldn't test it on rats. Hopefully, y'all know why they couldn't test it on rats. Maybe you don't know. Okay. Let's see you jump in. Maybe I'll tell you. Rats don't get COVID. You give a rat a vaccination, and they're not going to get COVID because rats don't get COVID. So that's why they didn't test on rats. Okay, it wouldn't work. Okay, they really needed to test it on people because that's who was getting COVID. Okay, I guess there were some, like, maybe a few cases of some other animals, but not rats, actually. But not enough to actually do anything with animals. They need to do it on people. And they really didn't, they didn't know 100% that it wasn't going to, like, destroy you or something. So what they did is they got a sample. And they got a sample of a whole bunch of people to volunteer to get the vaccination, even though it might have been dangerous or might not have worked at all. Okay, and next time I'll talk about a little more details about the control study they did. But right now I'm just going to kind of simplify it a bit. I'm not going to give you all the details. But they got a bunch of volunteers to, get the shot. And then they watched them for, some months. It's not the kind of thing that they can know if it works in a day, because, people don't get COVID on average in a day. It wouldn't work. And in fact, if they were doing it in a day, they would need way too big a sample size because, and we saw with confidence intervals, and in particular the central limit theorem, you need NP and NQ to be bigger than 5. Remember that? So if only 1 in 100,000 people gets it, you'd have to test over 500,000 people, which you can't do. That's way too many to do any kind of testing. Finding volunteers is impossible, and it's also, there's ethical issues. Okay, so instead what they did is they gave people shots and they waited a while. And let's suppose, just suppose 10% of the people are getting COVID on average. So then you have to have NP and NQ bigger than 5 just to use the central limit theorem, right? Or let's say it was only 1% would get COVID within, say, 2 months. Then you would have to do 500 people. They actually did 50,000 people, but they did 25,000 people to get the shot. Okay. And they did do a lot of biology to hope that the shot wasn't going to hurt anyone first. Okay, that you could do. They look at the chemistry, but that's not statistics. Okay, and then they wanted to see, of those people who got the vaccination, are they less likely to get COVID? Any questions on that? Okay, and by the way, I was not one of the people who was in the test group. Okay, by the way, I'm fully vaccinated, but I got vaccinated after it got approved, or after it got approved, as soon as I was allowed to get vaccinated. And so I definitely got vaccinated because I look at the statistic and I know it was a good thing. So here's what you do. The first thing you do is come up with what's called the null hypothesis and the alternative hypothesis. And what they did is they researched and they saw what percentage of just general people get COVID over the trial amount of time. And what they found out was 4%. 4% of just general people get COVID. Okay, that is called the null hypothesis. And the way you write it is H. H stands for the word hypothesis. And then you put a little 0 as a subscript. And I think the British got to it first. And do you know what they call the number 0 in Britain? Anyone know? Null. Yeah, null. And they call that's why it's called the null hypothesis. And they also, there's another word for it too that they use, and it's not. Okay, N-A-U-G-H-T, I believe. And so we'll say H not stands for the null hypothesis. And then you'll put a colon. So I want to let you know this piece, and this is for the rest of this entire course. We're talking every chapter we're going to be doing. So we're talking chapters 9, 10, 11, 12, and 13. You're going to be having this H not colon. Okay. And it's kind of a pain to do on Canvas, by the way. I think the easiest way is to do the equation editor. You do H sub 0, and then you leave the equation editor, then type in a colon, you go back into the equation editor for a new equation and do the rest. Okay, now, when it comes to COVID, either you get COVID or you don't get COVID. Do you agree? Okay. If you get that shot, the vaccination shot, and they do the trial for a few months, and in those few months, if you get COVID, you got COVID. If you don't got COVID, you're a no, you didn't get COVID. When you have a yes, no question, then we're talking proportions. Okay, and that's very important for the rest of this entire course. We're going to be thinking about what kind of question it is. And if it's yes, no, we're talking about proportions. Proportions use a P. Okay, any questions on that? Okay, the funny thing is, when I first taught this class, we didn't use a P. We actually used the Greek letter, confused the hell out of everyone. So I think I told you that a few weeks ago. And that's because the Greek letter for P is pi, and that is 3.14, etc. No one wants to do that. So they just went to P, and I like that better actually. So we're going to have P equals 0.04, which means the null hypothesis is that the population proportion of all people who could ever get the shot, the vaccination shot, that they would still have a 4% chance of getting COVID. So the null hypothesis means it doesn't work. It did nothing. It didn't help. Okay, then we have H sub 1. And there's actually two ways of writing this. H sub 1 you'll see more often. And that corresponds to the alternative hypothesis. The reason why they use 1, or a lot of people use 1, is it's a number after 0. But sometimes you'll also see H sub A for alternative. I usually do an H1 colon. So the null hypothesis is kind of, if your idea wasn't right, the vaccine didn't work, it's still 4% chance of getting it. The alternative hypothesis, what you're trying to show, is that the vaccination is working. And if the vaccination is working, then fewer than 4% of the people who are vaccinated are going to get COVID. Any questions on that? And the way you write fewer than 4% is P is less than 0.04. So I want to stop and make sure everyone understands, because this is really important. Okay, so I want to let you know, when you're doing hypothesis testing, the order is very important. The very first thing you do is you come up with your ideas and write down your null and alternative hypothesis based on your idea. And the idea of, say, Pfizer was that the vaccine works, which means fewer than 4% of vaccinated people will get COVID. Any questions on this idea? Okay. And again, this is a true story. Okay, and I'm not making this up. This is what really happened. Okay. Then the next thing you have to do is say, what errors could happen? And here's the different errors. There's a type 1 error. And a type 1 error means that you reject the null hypothesis, accept the alternative hypothesis, but the null hypothesis is true. Okay, that's a lot of words. So let me kind of explain what that tells you. You're going to accept that P equals 0.04. So you're going to accept, right? You're going to accept the null, you're going to reject the null hypothesis. You're going to reject that P equals 0.04. You're going to say, well, that's not true. P is not 0.04. You're going to accept the alternative hypothesis, which is that P is less than 0.04. You're going to say, we have evidence. We have statistically significant evidence that the proportion of all people who could ever get vaccinated who are going to get COVID is less than 4%. Okay, that's what you're going to say. But the null hypothesis was true. You're wrong. It's an error. 4% really do get COVID, even if they're vaccinated. And that's a bad thing, by the way. What bad things would happen if they had a type 1 error? Any thoughts in this case for COVID, for this COVID vaccination? Let's see if you can tell me what bad things would happen. If you're going to be able to say, hey, fewer than 4% of the people who get vaccinated get COVID. But you were wrong. Not less than 4%. Less than 4% getting COVID, that'd be great. You want fewer people. And it's not greater, it's actually equal to 4%. Okay, maybe you're not seeing what would happen. Remember, this is Pfizer, okay, or Moderna, whichever company you want to, think about, because they all had to do this. What would happen is that, and of course, the testers were not necessarily Pfizer and Moderna. They were Federal Drug Administration, FDA. You've heard of that, FDA approved. So FDA would do the testing and they would say, hey, fewer than 4% get COVID. And they would say that they're going to put their stamp on it and they're going to approve it. And they're going to say, this vaccination works. And what are they going to tell everyone in the country to do? Get vaccinated. And they're all going to get vaccinated and think that they're not going to get COVID or have a much smaller chance. They're going to go out and party. And then they're going to get COVID. That's pretty bad, isn't it? Okay. That's a type 1 error. Okay. And by the way, these errors are always bad. A type 1 or a type 2 error is never a good thing. Okay. Now, so what I wrote is the vaccine gets approved, but it doesn't work. Okay. People are going to get the vaccination. And I don't know about you guys. Another thing is when you guys, did you all get vaccinated? I hope so, by the way, because again, I'll talk about the p-value, what really happened and the whole, thing, but hopefully you got vaccinated because the statistics were very clear, by the way, and the FDA really did approve it. And years later, it still works. But if there was a type 1 error, then you would get the shot. By the way, the day after, especially my second shot, I was so exhausted. I don't know about you all. I couldn't even leave my bedroom. I was not mentally exhausted. I was physically exhausted. Okay. I didn't even eat that day because I was too tired to get out of bed and eat. I did computer program all day because I could at least do that because I didn't have to move my body much. But it was kind of a miserable day. And also, after I got vaccinated, you know what I did? I went and saw my family. My mom, who's like 84 years old. Well, imagine if I was still dangerous that I could have given her back COVID. Do you see that? And it could have been terrible. Okay, so that would have been really bad. Okay, so now let's talk about what's called a type 2 error. Type 2 error there is not enough evidence to reject the null hypothesis when the null hypothesis was false. So now what you're going to do is you're going to say, well, we did the test and we don't have statistically significant evidence to show that P is less than 0.04. But P really is less than 0.04, even though we didn't have evidence to show it. What is the FDA going to do if there isn't enough evidence to show that your probability of getting COVID doesn't go down after getting vaccinated? What is the FDA going to do? Yeah, they're going to say, forget it. You can't give this vaccination to everyone because it's not working. You don't have evidence to show it works, at least. Do you see? Okay, but guess what? He really is less than 0.04 and the vaccine really does work. You didn't have the evidence to show it, though. Is that a bad thing? Any thoughts? Yeah, all errors are bad. Yeah, it's terrible because what would happen is you have a vaccine that works and the FDA doesn't approve it. And you could have saved another 1 million people from getting COVID and dying, maybe. But the FDA didn't approve it. And those people died. Do you agree that's pretty terrible? Any questions on that? So these errors are both terrible. Do you agree? Honestly, it turns out a type 2 error is probably worse in this case, because having a vaccine work and not being able to use it is actually worse than getting vaccination and it doesn't do anything. Do you see? Okay, so the ramifications of a type 2 error is a vaccination does not get approved, but it really does work. Nobody gets vaccinated and 1 million people, more people, still die of COVID. Okay. Aren't you kind of glad that, I wouldn't say no one's getting COVID anymore, but we're kind of done? Okay, it's not the complete disaster that it used to be. Really, that's because of the vaccination. Okay. All right, so the next step that you have to do for hypothesis testing is decide on the level of significance. Do you remember we had to decide on a confidence level, whether it was okay to have a 5% chance of blowing it in your confidence interval and a 95% chance of getting it? So here, unlike the confidence interval with hypothesis test, you make a decision, you have to make the decision about the level of significance before you go and collect your data. Okay. So this is really important. And you make that decision based on the ramifications of a type 1 and a type 2 error. Okay, so let me talk about what these are. So the level of significance is the probability of a type 1 error. Okay. So you want that, you want it to be low, but there's a problem. If you lower the level, the probability of a type 1 error, then you have to raise the probability of a type 2 error. Okay, so again, you can't have it all. So that's an issue. So you have to see which is worse, the type 1 or the type 2 error. Okay, just to note, kind of the main standard is that you use a 5% level of significance if they're basically similar, if type 1 and type 2 error have kind of similar issues in terms of similarly bad. Okay. If the type 1 error is worse, then you want that to have a lower chance. So that means the level of significance should be lower. In our class, if the type 1 error is worse, lower than 0.05 will mean 0.01. If the type 2 error is worse, then you're going to let your type 1 error have a higher chance, so you can lower the type 2 error. And you're going to use 0.10 or 10%. So let me stop. Any questions about this idea? Okay, in the real world, it's a little more complicated than I'm saying it, but this is elementary statistics, so I can only go so far. Okay, any questions on this idea at all? This is really important. You have to be able to understand it. Okay, because we're going to be doing this for the rest of this entire course, not just this week. Okay, so in our case, I think a type 2 error is worse because there could be hundreds of thousands of additional deaths because you don't have a vaccination that's approved when you had a vaccine, when you could have gotten vaccinated. Okay. And that's worse than, to me, that's worse than having to sit in bed for a day feeling awful and when it didn't really do anything for you. Okay, and then maybe feeling a little extra too comfortable about being around people. So in my opinion, the type 2 error is worse, and if the type 2 error is worse, we're going to use a level of significance of 0.1. And by the way, anyone know how to read this letter right here that I just highlighted? It's a Greek letter. Yeah, it's the first letter of the Greek alphabet, which is alpha. The funny thing is, when I was a kid, everyone knew this letter, alpha, that it was the first letter of the Greek alphabet, because our #1 supermarket was called Alpha Beta. We knew the first 2 letters, just like everyone knows pi. But nowadays that supermarket's gone, I think. I don't think it even exists anymore. So a lot of people don't know that, but this is alpha. And alpha is the level of significance. Got it? Okay. And again, this order is really important. The first thing you do is decide what your null and alternative hypotheses are going to be based on your idea. The second step is to decide on the ramifications of the type 1 and type 2 error. The third step is to, based on the second step, which is worse, or if they're the same, you choose your level of significance, you choose your alpha. Any questions on these steps? Okay, the next step is actually in the real world is the hardest part. It won't be the hardest part for most of what you're doing because most of what you're doing is just answering test questions and stuff. But in the real world, the next step is to collect the data. So imagine you're, the FDA or whatever, then you have to go and you have to find 25,000 volunteers to get this vaccination that they don't even know if it works or not. Do you see? Do you know how hard it is to find 25,000 volunteers? Okay. Have you ever been a volunteer for something like this? Not as a COVID, but some kind of medical thing where they were testing to see if it worked? Yes or no? Have you been a volunteer? Okay. Let's see, I'll jump in, but I was a volunteer. When I was in college, I got paid to volunteer to, believe it or not, get some medicine. I had diarrhea and it was supposed to fix it. And I volunteered. They gave me $100. And that's how it was. So they need volunteers. Okay. So you got to collect the data. Okay. So that way they collected the data is they found 25,000 volunteers that could get the shot. Turns out they found 50,000, but 25,000 of them got the shot. I'll talk about next week what they really did. And then they watched those volunteers for months and saw what happened and gave them a test to see if they got COVID. And if they got COVID, then they were one of those that got COVID. If they didn't, they weren't one that got COVID. Okay. And that sounds easy to say. It's a lot of work to make that happen. Okay. And for other things, sometimes they'll do animals first, but this they couldn't. So people. All right. So so after you collect the data and you're used to this, is you put it into the computer. You put it into the computer. And you're going to calculate what's called the p-value. So let me show you what's up. This is a picture. We're saying the null hypothesis is that p is equal to 0.04. 4% of all people get COVID in that trial amount of time that they're watching. So given the fact that they had a large sample size, again, they had 25,000 people getting this, testing for the vaccination. 25,000 times 0.04 is definitely a lot bigger than 5. So that means that the sampling distribution is approximately normal. Do you remember that? That was a central limit theorem. And because the sampling distribution is approximately normal, we can draw this beautiful picture of the normal distribution. And what we want is we're trying to show that over here, p is less than 0.04. Do you see that? So that means in our picture, we're going to shade in where p is less than 0.04. Okay. And we want that probability to be less than 0.1. Okay. We want that probability to be less than 0.1. This is not an error, by the way, this 0.01, that's from something different. I'll get there in a bit. So the area to the left of this value needs to be 10% or 0.1. Then you can use the normal distribution calculator if you wanted to, and say, well, what value of X must there be so that this area is 10% or 0.1? Okay, any questions on that? Okay, and that turns out to be 0.01. So then what they did is they looked to see, they found out that that 0.01 is what they got, and the p-value turned out to be 0.004. Okay, the p-value turned out to be 0.004. So by the way, 1% of vaccinated people got COVID in this test sample. The area left of that was 0.004. That's the p-value. I do want to let you know that this is an example where we're trying to show that we're less than 0.04. We call that a left tail test. That's a left tail. Do you see that? There are times you do statistics and you're trying to show that things are greater than something. Then you do a right tailed and you do this side. There's other times you want to show things are different from something, and then it would be both tails or a two-tailed test. And that's how this p-value works. So we found the p-value. Once you find the p-value, you see if that p-value is less than the level of significance. And in this case, for Pfizer, okay, and by the way, for Moderna too, and for J&J, they found the p-value was less than 0.1. In fact, it was a lot less than 0.1. Okay. So once you have looked at that p-value and compared it with the level of significance, if the p-value is less than the level of significance, then you say, yes, I was right. My alternative hypothesis is correct. And here's the wording. And the wording is, there is statistically significant evidence. Those words have to be there. There is statistically significant evidence, absolutely necessary, to conclude that the population proportion, by the way, just like for confidence intervals, if you don't specifically say that you're talking about the population proportion, and you could talk about you could say the percent of all Americans, or all people in this case, all adults is what they're looking at. But if you don't use the word all or population, then I take off points. And for those of you some of you saw that I took off points for the confidence interval because it's the same idea. You have to have those words. So the population proportion of vaccinated people who get COVID is less than 0.04. And if you have statistically significant evidence to show that it's less than 0.04, that means you could say it works and the FDA will approve it. Any questions on that? Any questions? Okay, I do want to mention something. At this point, can there be a type 2 error? After this statement, can there be a type 2 error? The answer is no. Because a type 2 error means you failed to reject the null hypothesis when the null hypothesis was false. But here we didn't fail. We actually rejected the null hypothesis. We got evidence. Type 2 error is impossible at this point. But a type 1 error is still possible. Not likely, but it's still possible because we rejected the null hypothesis. And a type 1 error is when you reject the null hypothesis and the null hypothesis was true. Okay, the alternative hypothesis was false. In terms of medicine, a type 1 error often is called a false positive. Okay, and a type 2 error is called a false negative. Some of you might know it from pregnancy tests. That's kind of the most common one that people know about, is that when you take a pregnancy test, by the way, I've never taken a pregnancy test, but my daughter's mother took a pregnancy test, and obviously that was positive because guess what? She had a baby. And but if it's a false positive, that means you test and it's positive, but guess what? It didn't happen. So for pregnancy tests, it means that you tested it and it said that she was pregnant and she's not pregnant. False negative is the opposite. That means that you tested it and it said that she's not pregnant, but guess what? She was pregnant. Do you see that? Okay. And that's sometimes they'll call it false positive, false negative instead of a type 1 and type 2 error. So that might help because you might be more used to that. Okay. Any questions so far? Okay. So, by the way, after doing this, what did the FDA do? This is the real world, what really happened after they did this test. They approved it. Yep. They approved the vaccination and they said anyone in America, right, could get vaccinated who's an adult, by the way. This was for adults only. Because of all kinds of ethical things, you don't do children unless you have to. You do adults first. Because if something goes wrong, you don't want to screw up the children. So that's the reason. The other reason actually is COVID was killing older people. And there were very, very few children getting killed. That was the other reason. There were two reasons. Any questions so far? Okay, so now we want to say, what does it mean? What does it mean to say that we have a p-value of 0.004? What does that mean? Okay, so first thing, that's the area to the left of this. The area to the left of a normal distribution is a probability, right? What is the probability of? And let me type this out because I think it's worth it to type it right here. Well, maybe I'll type it here. Actually, let's do this. Get rid of some of these spaces so we have room. There, now there's room. Okay, so this is what we can say, is that if the population proportion of all vaccinated people who get COVID is 4% or 0.04. Okay, by the way, what I just did is I just restated H naught. Because H naught is P is equal to 0.04. In words, that is the population proportion of all vaccinated people who get COVID is 0.04. Or 4% of all vaccinated people get COVID. So you restate H naught. Any questions on that? That's the beginning of this. Then you say, and if another study of 25,000, because that's how many people got the vaccination shot, were vaccinated and watched, right? Or COVID tested, if you want to say. Maybe that's even better. At the end of the testing time, and maybe all the way through too, and through at the end. So during it at the end. Then there would be a. And then our p-value is 0.004. So as a percent, that's 0.4% probability. Okay, so there'd be a 0.4% probability that and again, of those that got vaccinated, only 1% got COVID. That fewer than 1% of them would get COVID. Whoops. Okay. So let me read this again, because this is very important. It's also one of the hardest parts of this, is that if the population proportion of all vaccinated people who get COVID is 0.04. Okay, so that's restating, that's saying if, and then you restate the null hypothesis. And if another study of 20,000, 25,000, that's sample size, were vaccinated and COVID tested during at the end of the testing time. Okay, so in other words, if you did another study, just like what you just did, then there would be a 0.4% probability. That was our p-value, 0.4%. That fewer than 1% of them would get COVID because that was the percent of our sample that got COVID. Any questions at all on how hypothesis testing works so far and anything that we've done? Okay, we also want to, so let me write down, actually, I should write down the instructions so you know what to do if you're asked. This is interpret the p-value.
Can you repeat it again? We got the p-value of 0.004.
Okay, you want me to repeat how I got which one?
The p-value of 0.004. Right below the graph, you have the bell curve.
Okay, the point, okay, that's when this is when they used the calculator basically to find the area.
Yeah.
That's the area under this curve. And that we'll use a calculator and we'll get there. I promise. I wanted to kind of show you a real life one, which means that I'm just going to do it for you. Does that make sense?
Yes.
And we'll get there with the calculator, but I want to do it without having to bother with the calculator, just kind of show you what happened. Yeah. So I'll show you how to get that p-value in a little bit. I promise. We still got like over half an hour to do some more examples. All right. Now, the next thing you want to interpret besides the p-value is the level of significance. And let me tell you the good thing, especially since I'm at a computer, is to interpret the level of significance, I start out with exactly the same thing up to the word A. I'm going to copy and I'm going to paste. And then I'm also going to get rid of some blank spaces so that I can see it all on one page. And that is if the population proportion of all vaccinated people who get COVID is 0.04, and if another study of 25,000 were vaccinated and COVID tested during the end of the testing, at the end of the testing time, there would be A. Now, our level of significance in this case was 0.1 or 10%. So I'm going to write 10% chance. Okay, or probability if you want, might be more formal. probability that, so now the level of significance, remember, is the probability of a type 1 error. So type 1 error means that it was true that 4%, and that's this first part, of vaccinated people get COVID, but you end up rejecting the null hypothesis saying that fewer than 4%. So that we would end up rejecting the null hypothesis. So that means concluding, maybe I'll even write falsely concluded, that fewer than 4% of all vaccinated people get COVID. During those months. I don't remember how many months they tested for. That's why I'm just saying those, because I don't want to steer you to some wrong thing. There were some months that they looked at people. Okay, I just want to let you know that the second part of the p-value interpretation refers to the sample of the 25,000 people. This is the them, whereas the level of significance refers to all people, not the 25,000. That'd be all people, maybe adults in the world. Any questions about interpreting the level of significance? Okay, so that's pretty much the standard for hypothesis testing. The funny thing is, you all learned this, not all the details, but you all learned about this in middle school. You didn't know when you did that? What you called it something else though. But it's standard in middle school. I know. I have no idea how old you are. Maybe there are some of you in middle school, but I doubt it. usually it's people that are, over 18. Sometimes I get a high school student or two. I don't know when you learn it. You heard of the scientific method? This is the scientific method. This is the statistics way of looking at the scientific method, but this is how the scientific method works. And you learn that in middle school. That's a national standard to learn that. Okay, doesn't mean you remember what you did in middle school, but you learned it once. Okay, any questions at all on this? All right, let's do another example. And I like this example because I don't know if any of you did it, but any guess on what I did on Saturday morning? Reading this example? The hint is you should all guess it after you read this example. Yeah, I tested the pH of streams that flow into Lake Tahoe. Okay, and by the way, not just pH. pH was one of the things I did. I actually tested the pH, I tested the salinity, I tested the dissolved oxygen, I tested the particulate matter. There's something in Tahoe called Snapshot Day. You heard of that? And actually, Snapshot Day is all over the country, but we do it in Tahoe, and I think we do it in Tahoe 1 month later because it's too much snow a month ago. But it's always done towards the end of May here. And what we do is we literally go in, and they get a bunch of volunteers, and I think there were like 100 of us volunteering and looking at all the creeks that flow into Tahoe, and we tested the pH. Okay, and this is done. And the question is, does the pH in streams that flow into Tahoe differ from 7.0? And again, if you haven't had chemistry, I'll tell you, pH, it's a chemical thing, tells you how acidic water is. And the pH of pure water is 7.0. Okay, and that's chemistry. And the question is, and if you have very far from 7.0, then if it's very low, it's acidic. If it's very high, it's called basic. And why you don't want it to be very far from 7.0 is that plants and animals can't live in it and it kills everything off. So it's really bad for the environment. Does that make sense? So what they do is they get a bunch of volunteers like myself. Okay. And not because I'm a statistician, it's just because I like to volunteer for things like that. And I actually went by Heavenly Valley Creek and Cold Creek. Those are the creeks I looked at on Saturday. And we tested it. And they won't have the collected data, information, and their hypothesis test for another couple months. So sorry, the class will be over by the time they do it, but they do it every year. And they've tested this before. And I was able to get their data from before, not from this year. All right, so the first thing is we write down what H naught and H1 are. H naught is mu equals 7. Notice on our last example, it was P equals something. Why is it mu this time? And anyone know? Yeah, it's the average. In particular, when you test for pH, you get a number. It's not a yes or no. Okay. In fact, I got 7.4. That was the number I got. 7.5 was the other one in the two creeks that I tested. They're numbers, they're not yes, no questions. Does that make sense? So that means we have a mu and not a p, and that's a disastrous mistake, by the way, on any kind of test, is to get that wrong. So make sure you can handle that and know that this kind of question is, what is the pH? Not, is there a pH or is the pH 7? It's what is the pH is what the test was. And then the idea is, if it's high or low, it's disastrous. If it's real high or real low, it's disastrous for the biology. So the the people who are working on this stuff care both sides, and that's why H1 is mu is not equal to 7. Whereas the last example, we wanted to show it was less than something, not greater than. We didn't care about greater. We wanted to be less than. We wanted to approve this vaccination. Here, not equal to on either side is bad. Do you see that? So this is called a two-tailed test because left and right of 7 are bad. Any questions on that so far? Okay, and then we go to the type 1 and type 2 error. All right, so if you think about type 1 error, remember the definition of a type 1 error is that you rejected the null hypothesis. So you accepted the alternative hypothesis when the alternative hypothesis was actually wrong. So in this case, the ramifications of the following, we have evidence, and I'll write statistically significant evidence to show that the pH differs from 7 when it is 7. Okay, what's going to happen if we show the pH differs from 7? What's going to happen if we show that pH of streams on average that go into Lake Tahoe is not 7? Anyone know? This is real world. If you live in Tahoe, you may have an idea. Okay, if you don't know, that's okay, I'll tell you. So then what's going to happen is the government is going to fund a very expensive project to mitigate the pH issue in the creeks. But it didn't need to be done. It was a total waste of money. Is that good? Would that be good if that happened? No. Okay. And waste of time too, but you're paying people. Okay. Now let's do a type 2 error. The type 2 error is we don't have evidence. To support the claim that the pH differs from 7. When it does. Will there be a problem? Any thoughts? Yeah, it's a terrible problem because what'll happen, no funding will be made. Will be put into it. And we'll end up having our biological or wild or plant and animals, so and the Lake Tahoe plant and animals will go extinct. That's pretty terrible, isn't it? Okay. So the next step, which do you think is worse? And this depends on your feelings, you know? Do you care about more about money or about the environment? I'll let you choose. Which is worse? So worse to waste a whole lot of money, or is it worse for the plant and animal life to go extinct? And again, this is really you. This isn't, you know, there's no right and wrong answer. Okay, so I saw at least the first person put in type 2 error. We'll go with that. And so if we think the type 2 error is worse, then we're going to use 10%. Any questions on that? If you're one of those that just don't want to, like, you know, waste your taxpayer money, and that was the most important thing in your life, then you would probably use a 1% or 0.01. If you think it's kind of balanced, then you'd use 5%. Any questions on that? Okay. All right, so let's go ahead and plug in some data. Let's suppose, I don't think I give all the data in here. Maybe I didn't. I better put something, I'll make it up. I'm trying to remember what it was. We have X bar was 6.4, and we need to give some more information. So let's say X bar was 6.4. Let's suppose that the S was 1 point. Let me see something. Let's say S was equal to 2.5. And let's say N Let's say S was equal to 3.5, just for fun. And let's say N was equal to 15. Okay, so the first thing, do we have to make any assumptions? To find a p-value? What are the number of sample? 15. There it is, N equals 15. N is the number of sample. Okay, the answer is yes, we have to make an assumption. N is 15, that's less than 31. That means we must assume that the distribution is normal. Right? It's not greater than 30, it's less than 31. Those are the same things. So we must assume the distribution of pH levels is normal. Okay. If you don't want to assume that, then you need a bigger sample size, greater than 30. Does that make sense? Okay. By the way, if it were proportions, then don't use 30, then it's, or 31, use NP and NQ greater than 5. All right, so now we're going to find the p-value. So to find the p-value, any guess on what I'm going to have to do? Yep, calculator. So let's go to the calculator. What do you think? What do you think we're going to use? What number? Yep, number 14. We're doing a hypothesis test for a mean, and we have statistics. We don't have data. So I click that. Do we know sigma? Yes or no? So do we know sigma? Okay, no, it's not the S value. It turns out we don't know sigma. We know S. And in the real world, you never know sigma. But some other faculty wanted this here, so I put this in. But again, you could do that in theory at least. Okay, and then you put in your numbers. S. So now we have to go and see. We have S. Was 3.5. We have X bar. X bar was 6.4. We have N. N was 15. And this mu naught, that is our number in H naught. So in this case, it's 7. Any questions on that? So that's 7. And then less than, greater than, or not equal to. So again, if you go to H1, you see the not equal to. So I put not equal to. And I hit calculate. All right, I hit calculate, and our test statistic, T is called the test statistic. It's T because we needed to use the student's T distribution because we did not know the standard deviation of the population. Okay, and we're talking about a mean here. So the test statistic is negative, let's call it 0.66. Maybe I'll do, because your assignments are going to do 4 decimals, 6639. The p-value was 0.5175. Any questions how I use a calculator to get these? All right. By the way, the picture here is a normal distribution, because we assumed. 7 is our hypothesized mean. And then X bar was 6.4, which is, by the way, 0.6 away from 7. So the other side will be 7.6. Okay, sometimes you can be asked for that. So the conclusion is there is, what do you think? Do we reject the null hypothesis, or do we fail to reject the null hypothesis? Our p-value is 0.5175. Here's a hint. That's greater than 0.1. That's our alpha. Yeah, we fail to reject, okay? Because you need to be less than the level of significance to reject. So there is statistically insignificant evidence to make a conclusion that the population mean, notice it's a mean this time, and it's population mean, pH of streams that flow into Tahoe. Differs from 7, differs from 7. Any questions on that? Any questions? All right, so the next is, what does it mean to have a p-value of 0.27? Okay, this is going to be tough for a lot of you. So let me show you what's up. So we start out with restating H naught, if, with the word if. If the population mean pH of streams that flow into Lake Tahoe is 7, and if another 15 streams were tested for pH, or maybe measured, then there would be a. Does it sound familiar so far? I mean, it's not exactly the same words as the one we just did, but it's the same idea. So there would be a, and our p-value, I should say 5175. There would be a, let's call it 52% chance that the sample mean pH would either be less than 6.4 or greater than 7.6. Any questions on how I got the 7.6? because that a lot of people stumble on that. Any questions? Okay, so there's no questions. Let me move on. If we want to interpret the level of significance of 0.1, remember, we copy everything up to the A. So if the population mean pH of streams that flow into Lake Tahoe is 7, and if another 15 streams were measured for pH, there would be A. Now it's a 10% chance that we would end up falsely concluding that the population mean pH of streams that flow into Tahoe is not 7. Any questions on this idea? Okay, let me do another example. Suppose you want to see if women are not drinking the recommended 2.7 liters per day on average. Okay, that's of water, by the way, or of good fluid, I guess. Then H naught is mu equals 2.7. And H1 is mu is less than 2.7. Because, by the way, what you're really worried about is that they're not drinking enough. Okay, no doctor says you're drinking too much water. It's always not enough. So that's why it's a less than in this case. Okay, let's suppose we decided on a 0.01 level significance, because I want to get to the part that's new for us. And let's suppose this is what's given. They've given the data from the survey that was done on the amount of liters a day women drink. They asked all these people. Any questions on that? All right, so now we're ready to go to the calculator. And what calculator number do you think I'm going to use? Yeah, this is 15. By the way, I didn't do it for you because we only have so much time. But on the first example, that would have been to hypothesis test for proportion if we had all the data. But here we have hypothesis test for a mean with data. And then I put in the data. I just copied and pasted it. We don't know a standard deviation, so leave that blank. We have a lesson. Our mu naught, again, was 2.7. And hit calculate. Okay, so by the way, here's X bar. Here is S. And the test statistic is negative 1.9365. The p-value was 0.0306. Any questions on that? All right. Do we reject or do we fail to reject? What do you think? I don't see y'all jumping in. All right, let me give you a hint. Here's our level of significance. Yeah, there we go. Yeah, so our level of significance is 0.01. 0.0306 is greater than 0.01. So that means we failed to reject. By the way, had we used a level of significance of 0.1, you would have rejected. But you're never allowed to change after you collect your data. Okay, you have to pick your levels of significance before you collect your data, and then you're stuck with it. Okay, and that's called ethics. So there is statistically insignificant evidence. To make a conclusion. Okay, or maybe to conclude, even better. That, okay. And then I could just do this. And now I better write this, that the population mean amount of fluid, or maybe water, that women drink is less than 2.7 liters per day. Any questions at all on the conclusion? Any questions? Okay, I want to give you a template so that you kind of get the idea of, how these always work. So there is statistically significant, maybe I'll even write, sometimes it's insignificant, sometimes it's significant, depending what you got, evidence to support the claim that the population, it'll either be mean or proportion, and then it's whatever your H1 is. So that's kind of a template for the conclusion. The template can also be insignificant. So like I said, I'm not even going to put that one in because we've got insignificant and significant. And the p-value interpretation template is if, and then you rewrite the null hypothesis true in words, about what the study is, and another sample of however many that you took was taken. Then there would be whatever the p-value is, probability, that, and then the results of the new study would be at least extreme as a result of this study. Don't write that in. That's the idea, right? So over here, for example, we had, there would be the chance that the sample mean pH would be either less than 6.4 or greater than 7.6. That's being at least as extreme in this case. And then for the level of significance template, if, and then you read null hypothesis is true, okay? And if another sample of how many was taken, same as the p-value template, then there would be A. And then it's a level of significance probability that the new study would result in falsely concluding, and then you restate the alternative hypothesis. Any questions at all on these templates? I like to give you those so you kind of know what's going on. Okay, I want to let you know, we don't have time to do lots of examples, but I had them just in case. So there's more examples, but I want to give you the secret word. Okay, we're not done yet, but I want to give you the secret word anyway. The secret word is insignificant. Because if you fail to reject, then you have insignificant evidence or insufficient. You have two choices, and you can use either word, those words. So insignificant is the secret word for today. Okay, now what I want to do is I want to go over project 2 a little bit. And let's go to the syllabus. And I want to show you a few things. We go to the projects. Okay. And what it says for project 2 is students will conduct a survey and construct a confidence interval and perform a hypothesis test. Okay, you're not ready yet because it's really chapter 10, but at least you know what these are. Each project will include the results of a narrative describing the data collection, assumptions made, background information, how the data was analyzed, and conclusions. Okay. You must use a spreadsheet program. And again, I created a spreadsheet program. And next week, I'll show you how to use that. We're not ready yet because we haven't learned that chapter 10 yet. Okay. And you must show your computer results in the project. Okay. The relevant part of the spreadsheet must be copied and pasted in the project. And then this is for both projects, but I want to remind you again, is that double spaced, you should use 12-point font, you must work in pairs or trios, so 2 to 3 people in a group. And you can use the same group if you want, you can use a different group if you want, but you have to have 2 or 3 people. It's a disaster if you work by yourself, by the way. Nobody ever, I don't think anyone's ever passed working by themselves. So don't work by yourself. Okay. And again, what do you do if you don't have a partner or you want to change your partner? What should you do? Any guess? What do you think you should do? I don't see y'all jumping in. You should go to the discussion board. And you click on the Project 2 discussion forum. And if anyone wants to look for a project, please let me know. Okay, you put that in. Okay. So that's just a note that's really important. And then you get a partner. Okay, or partners. 3 is best. Less work if you do 3. Also, if someone drops out, then you can still, it kind of means, okay, better is to post it in the discussion board. Okay. And then if we go back to the syllabus again. So I will look at your rough draft if you email it to me by the Thursday at 8 a.m. before it's due. That makes a huge difference, by the way, because then I can show you errors that you made. And then you can fix those errors. Okay. So very important for timeline. And just note, the project is due by June 25th. So that's a Sunday, by the way. And so the Thursday would be 3 days before that, which would be June 22nd. And, again, 8 in the morning. So I'd recommend, maybe Wednesday, June 21st or Tuesday, June 20th, and get that sent to me. Does that make sense? Okay. And then I'll take a look at it and give you suggestions, just like I did for those who did it for project 1. Any questions so far? Okay, so that's the main thing. Just to know, we're not ready to fully understand all this yet, but I'll read some of it anyway, because we still can. And that is, if I click on this project 2 click, it gives you some information about project 2. And I'll say it, and I'll talk about more next week too. So project 2, we're going to use confidence interval and hypothesis testing to show support or lack of support for a research project. Okay. And just like the last one, you should have a client, and that'll be your audience that you're sending it to. Okay. You must first decide what you're interested in researching, then design your study to collect the data. Also identify a client who will be making the decisions based on your results. I should say based. Next, analyze your data to see what it tells you and whether it supports your hypotheses. Any questions on that? Okay, so again, you understand what confidence intervals are, you understand what hypothesis tests are, but you're gonna have to do a comparison study, which is next week. So I can't tell you all the differences. You should just discuss the sampling technique lightly. It's not as important as project 1. This is not project 1. Notice I don't tell you what you have to use. If you want to use convenience sampling, that's fine. This one doesn't even have to be a survey. It could just be doing, looking at some data that's been collected. Okay. So that's important. And just note, if you can get the data on the entire population, then this won't work, because there'd be no reason to do a confidence interval hypothesis test if you can get data on the entire population, because then you just know for sure. So this is something that you're not going to be able to easily get data on the entire population of. Okay. Your sample sizes, which I'll talk about next week, must be greater than 30. And that we've seen before. Okay. So that's all important. You must have a list of summary statistics and interpretation of each. And again, we'll talk about this next time, because the statistics from the differences, which were this next week. You can't use someone else's study. You can use data that hasn't been studied yet. Does that make sense? So you're not just copying someone else's study. So if you use a journal study, then that's just saying all you're doing is copying and pasting their article. So you're doing your own study. Okay. So that might be something like, I don't know, I'm just making some stuff up since it's baseball season. Let's suppose you want to say, the average game, do the American League teams have more hits than the National League teams? Okay, that's something that I don't think you can get the entire population of, but you can go and you can find 31 games from the National League and 31 games from the American League and grab that data. Does that make sense? Okay. So again, it's data that you can get. Okay. And that you can't get all of it, but you can get some of it not too badly. Okay. And there's lots and lots of examples. You should post your hypothesis, and you should post your idea and your sampling that you're going to do, how you're going to get your sample. Post that on the Project 2 discussion board. And then I'll look at it and let you know if it's going to work. Okay. And again, I would do that. Again, that would be after next week. Don't do that now because you're not ready yet. But after next Tuesday will be our webinar in chapter 10. So it should be at least after next Tuesday. Don't post until after then because you're not ready yet. So I can't give you all the details because that's next week. But I wanted to give you kind of a heads up. Any questions at all on kind of these ideas? And we'll do more next week on this, I promise. Okay, I do want to mention one more thing, and this is important. If you go to the discussion board again, and you go to week 7 hypothesis testing, so the discussion post that's due this week, then this is different than one you've done before, is you're going to find an article, and you've done that before, you found articles, but this one must be published in a journal. Okay, so we're not talking about the project anymore. Now we're talking about just this week's assignment. It must be published in a peer-reviewed journal. Okay, so don't go use CNN, for example. That is not a peer-reviewed journal. So let me show you how you find peer-reviewed journals. You go to the internet, and you go to Lake Tahoe Community College, and you scroll down, and you go to our library. So it's the library link. Then you go click on Find Articles. Then you click Academic Search Complete. And then you can find an article of what you might be interested in. Okay. And a good percentage of articles, and by the way, if you look at this, Where was it? It was there. Okay, and it says that you have to have a peer-reviewed journal article that involves hypothesis testing. A very large percent of peer-reviewed articles involve hypothesis testing. So it's actually not that hard to find in whatever you're interested in. May not be your first look, but I would guess within 3 or 4, you'll find it often your first look. Okay. And then you find what you're interested in. So I don't know. I'm interested in hiking. That's what I like to do. But you do what you want to do. Hit search. Oh, you know, I forgot. Let's see. We want peer reviewed. You have to click peer reviewed. And the first article, downhill hiking improves low-grade inflammation, triglycerides, body weight, and glucose tolerance. I'm going to click full HTML text, HTML full text. Okay. And guess what? P-value. This one had it. Do you see? So that has a p-value. So that means they must have done a hypothesis test. And by the way, I did not prepare for this ahead of time. I literally just randomly picked the word hiking and it worked. I didn't get lucky. It usually will. You'll usually find a p-value. And then you can read the article and it'll talk about it. Okay. And often they have many p-values like they do here. Here's another p-value. Here's another p-value. It means they do multiple hypothesis tests. Okay, then what you're going to do is do not paste the link. What you want to do is you want to paste the title of the article into your initial post. The link doesn't work, it turns out. You say, I found this in the library, search, and this is the title. Go look for it. If it's a very long journal article, then you might want to talk about the page number or where it is instead of the page number. Like, for example, we found it here under results. So you would post, you can find it under results. And that way you're guiding your partners and your fellow students how to find where the p-value is. Okay, any questions on that idea? I figured I'd show that because a lot of people haven't used the library search engine before, and that's how you use it. Okay, you don't have to use the library search engine, but it's much harder to find peer-reviewed articles than any other way. And this is the nice thing about our library if you're a student, and you will have to, I'm already logged in, but you'll have to log in with your name and username and password that you log in to Canvas, for example. It's the same username and password, whatever you use. Any questions on that? Okay, if there's no questions, what I'm going to do is I'm going to call it a night. And but I will be happy to answer questions after we close it off. So I'm going to stop the recording.